Let's kick things off with NLP, or natural language processing. Essentially, it's all about teaching computers to actually understand what we're saying and writing. Think of it as giving machines the ability to read and interpret human language. We start by breaking down text that's called tokenization into manageable pieces like individual words. Then, we need to figure out what each word is, which is where part of speech tagging comes in, identifying whether a word is a noun, verb, or adjective. And finally, we can identify specific entities, such as people and places, within ER. NLP uses various techniques from simple rule-based systems that follow predefined patterns to powerful statistical models and, increasingly, deep learning methods like the transformer architecture, which are really changing the game. Okay, let's talk about getting our text data ready. The first step in any NLP project is preprocessing, essentially cleaning up the raw text. Think of it like prepping ingredients for a recipe. First, we use something called tokenization to break down the text into individual words or units. Then, we often lowercase everything so that they are treated as the same word. Next, we remove common stop words like a, and that don't really have much meaning. Finally, techniques like stemming or lemmatization can help reduce words to their root form, making things more consistent. Okay, let's talk about how we get started with these AI systems. It all begins with breaking down text or images into smaller pieces. This process is called tokenization, and it's like preparing ingredients for a recipe. We can split text into individual words, but that doesn't always work well, especially when dealing with complex sentences. Subword tokenization breaks words into smaller parts, a really clever technique that helps handle tricky cases. And then there's character tokenization, which treats each letter as its own unit. Ultimately, the best method depends on what you're trying to achieve and the type of data you're working with. Okay, let's talk about stemming and lemmatization. Both are techniques we use to clean up text data before feeding it into our NLP models. Think of them as getting words back to their basic form. Stemming is like a quick chop, it just removes prefixes or suffixes based on some rules. It's fast, but can sometimes lead to strange results that aren't actual words. Lemmatization, on the other hand, is smarter. It looks at the meaning of the word and tries to find its dictionary form, considering the surrounding context. So running, ran, and runs all get reduced to run. It's more accurate, but takes a bit longer. Okay, let's talk about stopword removal. Think of these as the common words that appear all over the place in text, but often don't really tell us much about the core meaning. Removing them can actually make a big difference in a lot of NLP tasks like sentiment analysis or topic modeling. We do it to reduce noise, improve accuracy, and speed up processing. There are a few ways to handle this. You can use pre-built lists, create your own rules based on length of patterns, or even learn these stopword lists for massive amounts of text data. Okay, let's talk about the bag of words model. It's a really important starting point for understanding NLP. Basically, it's a way to represent text as just a collection of words, ignoring everything else like grammar or sentence structure. Think of it like a word frequency count. It breaks down your text into individual words, then builds a list of all the unique words. That's the vocabulary. Finally, each document is turned into a vector, where each number in the vector tells you how many times a particular word appears in that document. It's a simple but surprisingly effective technique for many NLP tasks. Let's talk about TF-IDF. It's a really clever way to figure out which words are most important in a piece of text. Basically, it measures how often a word appears in a document. That's term frequency. But then, it also considers how rare that word is across all the documents you're looking at. If a word shows up only in a few documents, it's considered more important than a super common word like the. By multiplying these two scores together, we get a TF-IDF score, and that tells us just how significant each word is to a specific document within the whole set of texts. It's used everywhere from search engines to help you find what you're looking for, and even in things like summarizing text or understanding someone's feelings about something. Okay, let's talk about word embeddings. Think of them as a way for computers to actually understand what words mean, rather than just treating them as random symbols. We convert each word into a list of numbers of vector where words with similar meanings are positioned closer together in this space. There are several popular techniques like word2vec and GloV which learn these embeddings from massive amounts of text data. Fast text is particularly good at handling unusual or complex words. Basically, by representing words as vectors, we enable our NLP models to perform much better on tasks that require understanding the meaning behind the text. Okay, let's dive into word2vec. It's a really clever technique for turning words into numbers, specifically vectors. Think of it like creating a map where similar words are placed close together. There are two main ways to do this, SIBO and skipgram. SIBO tries to guess the target word based on the words around it, like filling in the blank. Skipgram does the opposite, it guesses the surrounding words given a single, central word. Both methods use a simple neural network and learn by predicting relationships between words within a massive text collection. Let's dive into GloV. It's a technique in NLP that helps computers understand the meaning of words, not just as individual tokens but in relation to each other. Think of it like building a map of how often words appear together. We call this a co-occurrence matrix. Then, using clever math, GloV factors this matrix down into smaller vectors for each word. These vectors capture these relationships, and the goal is that the dot product between two words vectors will roughly equal the log of how many times they appeared together in the data. It's faster to train than some other methods, and often provides more intuitive insights into how words connect. Let's talk about fast text. It's a really clever way to understand words and their relationships. Unlike some earlier methods that just looked at whole words, fast text breaks them down into smaller pieces, specifically character engrams. Think of it like building words from individual letters. By considering these characters, it can handle words it hasn't seen before, which is a huge advantage. Plus, because it understands how words are formed, like adding prefixes or suffixes, it captures similarities between related words in a really intuitive way. And the best part? It's amazing for multiple languages. Okay, let's talk about contextual word embeddings, a really important step in modern NLP. Think back to older methods like word2vec and GloV. They gave every single word just one asterisk vector representing its meaning. But that's not always accurate. The same word can have completely different meanings depending on how it's used, right? Contextual embeddings solve this problem. Models like Roberta and Elmo create a unique vector for each word asterisk within its sentence asterisk. It's like they're saying, okay, I'm looking at this word in this specific context, so here's how it should be represented. They use something called transformers with self-attention to do this really effectively. For instance, the word bank can refer to a financial institution or the side of a river, and these models capture those distinct meanings. It's a huge leap forward in understanding language. Okay, let's talk about Elmo. It's a really clever technique in NLP that changes how we think about words. Traditional word embeddings like word2vec give each word just one fixed meaning. But Elmo is different. It creates different asterisk meanings for the same word depending on the sentence it's used in. It does this by using a powerful model called a bidirectional LSTM, which looks at the text both forwards and backwards to understand context. Think of it like this: bank can mean a riverbank or a financial institution. Elmo figures that out. The embeddings are combined with weights learned during training, so they're really helpful for improving performance on many different NLP tasks. It was a huge step forward because it showed us how crucial contextual understanding is for computers to truly understand language. Okay, let's dive into the architecture of BERT. It's a really clever design. Basically, BERT is built on the transformer architecture, which uses something called attention. This allows it to look at the words in a sentence at once and figure out how they relate to each other, not just processing them one by one like older models. It was trained on a huge amount of text. First, think Wikipedia and a bunch of books to learn general language patterns. Then, you can fine-tune it for specific tasks, like answering questions or classifying sentiment, making it incredibly versatile. Okay, so let's talk about the GPT family. It started with GPT-1 back in 2018, a really important step that introduced the transformer architecture. Then we saw a huge jump with GPT-2 in 2019, which was much bigger and could do some pretty impressive text generation. GPT-3 arrived in 2020, and it was massive, think billions of parameters. It was amazing for its ability to learn from just a few examples. We then moved into the GPT-3.5 era with Instruct GPT, which focused on making these models better at understanding what we want them to do. Finally, in 2023, we got GPT-4, and it's a game changer because it can even understand images alongside text. It's been a really exciting evolution. Okay, let's dive into how transformers work for natural language processing. Basically, they are a major shift from older models like LSTMs. Instead of reading words one after the other, which can get slow and miss context, transformers use something called self-attention. Think of it like this: each word in a sentence pays attention to every asterisk of the word in the sentence to understand its relationships. It's all done through 3 matrices that calculate how important each word is to every other one. The architecture has an encoder, which processes the input and creates representations of the words, and a decoder which generates the output. Because they don't have to process things sequentially, transformers are much faster than previous models. Okay, let's dive into attention mechanisms, a really important part of how modern language models understand text. Basically, instead of just reading words one after the other in a sentence, these models learn to pay attention to the most relevant parts for what they're doing, like predicting the next word or figuring out what something means. It's like your brain: when you read, you don't treat every single word equally. There are different kinds of attention, including self-attention, where a model looks at its own sentence to figure out relationships between words, and multi-head attention, which lets it look for multiple types of connections simultaneously. This has been huge in making models like transformers so powerful. Okay, let's talk about next sentence prediction. It's a really clever technique used primarily with transformer models like BERT. Essentially, the model is given 2 sentences, one it needs to understand and another that could follow it. The goal isn't just to recognize words, but to actually figure out if they naturally go together in conversation or text. It's like a test of whether the sentences make sense in context. This training pushes BERT to really grasp how language works, understanding relationships between words, and making sure everything fits together smoothly. It's a key part of what makes these models so powerful. Okay, let's talk about sentence embeddings. Think of them as a way to translate words and sentences into numbers, specifically dense vectors. These vectors capture the meaning of a sentence, not just its individual words. Models like sentence transformers are trained on huge amounts of text, learning these relationships so they can represent sentences numerically. The cool thing is, sentences with similar meanings will have vectors that are close to each other in this space. We measure how similar they are using something called cosine similarity. Basically, it tells us how closely aligned the 2 vectors are. This opens up a lot of possibilities, like being able to find documents or paragraphs that mean roughly the same thing, even if they don't use the exact same words. Okay, let's dive into document embeddings. Basically, these are numerical representations of entire text documents, like a whole article or a long email, that capture the meaning behind them. Think of it as translating words into numbers so computers can understand relationships between documents instead of just looking for keywords. We've got a few popular techniques: Doctorvec, which learns embeddings by considering both individual words and their context in a document; sentence transformers, which are pre-trained models that do an amazing job generating these embeddings using powerful architectures like BERT; and then as TF-IDF, a more traditional method that helps us measure how important certain words are within a specific document. You can see a quick example of using sentence transformers in Python. It's surprisingly easy. These techniques really open the door to some cool AI applications, like finding similar documents or building intelligent search systems. Okay, let's talk about how we get computers to understand what text asterisk means asterisk. One of the first steps is called text classification. Basically, it's like teaching a computer to sort documents or sentences into different categories. Think spam vs. not spam, positive review vs. negative review, or even identifying news topics. There are several ways to do this. We've got naive Bayes, which is a really simple and quick method that uses probability logistic regression, which looks at how features relate linearly, and then support vector machines, which can be more powerful when you have lots of different words and patterns. But before any of these algorithms can work, we need to turn the text into numbers. That's where feature extraction comes in. Techniques like bag of words or TF-IDF help us represent the text numerically so the computer can learn from it. Got questions? Let's move on. Let's talk about named entity recognition, or NER. It's a really important part of NLP. It's basically like highlighting the key players in a piece of text. We're talking about identifying things like people, organizations, locations, dates, and times. I've included a simple table to show you some common entity types and examples. There are several models used for NER, from older techniques like CRF to powerful modern approaches using RNN and especially transformers like BERT. And of course, NER has tons of real-world applications, everything from analyzing news stories to building smarter chatbots and even helping process medical records. Okay, let's talk about part-of-speech tagging, a really important piece of the puzzle in NLP. Essentially, it's like giving each word in a sentence its grammatical role. We label things like nouns, verbs, adjectives, the building blocks of language. It's surprisingly complex because words can have different meanings depending on how they're used. We use models like hidden Markov models and conditional random fields to learn these patterns from tons of label data, basically teaching computers what's likely to go with what. So, cat is a noun, sat is an action. It's all about understanding the sentence structure. Okay, let's dive into constituency parsing. It's all about understanding how sentences are built from smaller parts like a grammatical family tree. We use phrase structure rules to define how phrases combine, starting with simple building blocks and working our way up. There are different parsing methods, like recursive descent and chart parsing, which help us efficiently build these parse trees representing the sentence's structure. You can imagine it as breaking down a complex sentence into manageable chunks, showing you exactly what each word and phrase contributes to the overall meaning. It's a really important step for NLP because understanding the sentence structure is key to things like machine translation and sentiment analysis. Okay, let's talk about summarizing text. How do we get the gist of something really long without having to read every single word? There are a few different ways computers can do this. One approach is extractive summarization, where it basically picks out the most important sentences directly from the original document and throws them together. Think of it like highlighting key passages. Then there's abstractive summarization, which is more sophisticated. It actually rewrites the text, creating new sentences that capture the main ideas almost like a human summary. We also have simpler methods like taking just the first few paragraphs or scoring each sentence to see how important it is and then selecting the top ones. It's fascinating how much progress has been made in this area. Let's talk about extractive summarization. It's basically like highlighting the most important parts of a text and just copying them over to create a summary. Instead of trying to rewrite sentences, which is what abstractive summarization does, we're looking for the sentences that already contain the key information. There are a few ways this works, like using something called TF-IDF, which looks at how often words appear in a document and how rare they are across all documents. Another method is text rank, which is inspired by Google's PageRank algorithm. It basically figures out which sentences are most connected to other important ones. And LexRank is similar but uses a different way of measuring those connections. Think of it like pulling out the essential facts directly from the original text, without changing the wording at all. Okay, let's dive into abstractive summarization. It's a really interesting area of NLP. Basically, instead of just pulling out key phrases from an article to create a summary, abstractive models understand the text and then rewrite it in their own words. They are like skilled writers who can condense information while maintaining its essence. These models typically use sequence-to-sequence architectures, often based on transformers, which leverage attention mechanisms to focus on what's most important. And they are usually trained with a combination of massive pre-training and then specialized fine-tuning for the exact summarization task you need them for. It's a smart approach. Okay, so let's talk about question answering systems. They're all about getting AI to understand what you're asking and then give you a helpful answer. The basic idea is that we need to first find the relevant information, often by searching through a bunch of text, like documents or web pages. Then, the model needs to actually read this information and pull out the specific answer you're looking for. It's a bit like having a super smart assistant who can quickly find and summarize key facts. We use techniques like information retrieval, which is basically a really advanced search and reading comprehension models that understand how sentences relate to each other. Powerful language models like BERT and transformers are the workhorses behind these systems, and something called RAG retrieval augmented generation combines search with generating text for even better answers. You'll find QA systems popping up in all sorts of places, from chatbots helping you with customer service to tools assisting doctors with diagnoses. Okay, let's talk about building a chatbot. Think of it like this: you need to understand what the user is saying first, then figure out how to respond appropriately, and finally deliver that response in a way they can easily understand. We start with natural language understanding, or NLU, which helps us figure out what the user wants. Then comes dialogue management, really the brain of the chatbot. It decides what to do next based on everything we've gathered so far. After that, we generate a response, and finally, we deliver it through the right channel. It's usually structured like this: you have your user interface, then NLU for understanding intent and entities, followed by a dialogue manager to control the conversation flow, a way to generate responses, and often access to an external knowledge base or API. Okay, let's dive into dialogue systems. There are really two main types. First up, you have open domain systems. Think of them as conversational robots that can chat about pretty much anything. They are powered by massive language models like ChatGPT, and they generate responses on the fly. But it's not always perfect. They sometimes struggle with staying on track or ensuring their information is accurate. Then we have task-oriented systems, which are designed for a specific job like booking a flight or ordering pizza. These are more structured, using techniques to understand what you want and guide you through the process. Okay, let's dive into how we figure out the feeling behind text, what people are really saying. We have a few different ways to tackle this. First up are lexicon-based approaches. Think of these as pre-built dictionaries that assign scores to words based on whether they are positive or negative. Tools like Fader are super helpful here, because they even account for things like really good versus just good. Then we move into machine learning models like Naive Bayes and SVM learn from examples of text labeled with sentiment. Finally, deep learning using RNN, LSTMs, and especially transformers like BERT are giving us incredibly accurate results by understanding the context of words within a sentence. Okay, so let's talk about how we can automatically find the main themes of topics within a bunch of text data. This is where topic modeling comes in. It's like giving an AI detective a pile of documents and asking it to tell you what they're all about without you having to label everything yourself. One really common method is called LDA, or latent dirichlet allocation. Basically, each document gets broken down into a mix of different topics, and each topic is described by the words that frequently show up in it. Another technique is NMF, which takes a slightly different approach to figuring out these connections between documents and their themes. When choosing how many topics you want to identify, it's really important to pick the right number. Too few and you miss important details, while too many and things get confusing. We also use metrics like perplexity and coherence to help us evaluate how good our topic modeling is. Okay, let's dive into LDA. It's a really cool technique for understanding what's really going on in a collection of text. Essentially, LDA helps us automatically discover the main themes or topics present in a set of documents. Imagine you have a bunch of news articles. LDA can figure out that there are clusters around things like sports, technology, politics, and so on, even if you didn't tell it to. It does this by assuming each document is made up of a mix of these hidden topics, and each topic itself has a certain probability for different words. So a football would be more likely in the sports topic, while algorithm would be more likely in the technology topic. It's all about uncovering those underlying structures without you having to manually label everything yourself. Let's dive into non-negative matrix factorization, or NMF. It's a really clever way to reduce the complexity of data while keeping things meaningful. Essentially, it breaks down a big matrix. Think of all those word counts in a document collection into two smaller matrices. These new matrices only have positive numbers, making them easier to understand and interpret. The columns of one matrix represent what we're calling components or underlying concepts, like topics, and the other matrix shows how much each concept is present in the original data. It's super useful when you want to find hidden patterns without losing any important information. Okay, let's dive into how machines actually translate languages. Back in the day, we used to build translation systems by hand, creating tons of rules for every single word and grammatical structure. That was a huge undertaking. Then came statistical machine translation, where computers learn patterns from massive amounts of translated text. But really, the game changer has been neural machine translation. These models use artificial intelligence to understand context and produce much more fluent and natural translations. It's like they can actually think about what's being said. Okay, let's talk about neural machine translation, NMT. Think of it as a huge leap forward from older translation methods. Instead of painstakingly defining rules or relying on predefined phrases, NMT models actually learn to translate directly, just like we do. They take an English sentence and transform it into its French equivalent, for example. The core idea is that the model learns an internal thought vector way of representing the meaning of the entire source sentence. Then the decoder uses this representation to build the translation word by word. Okay, let's talk about sequence-to-sequence models, a really important concept in AI. Imagine you want your computer to translate English into Spanish. A sec-to-sec model is how we do that. It's like having an encoder that reads the English sentence and creates a summary of its meaning, a context vector, if you will. Then, a decoder takes that summary and builds the Spanish translation, one word at a time. The clever bit? Attention mechanisms help the decoder really focus on the important parts of the original English sentence as it's generating each translated word. You'll often hear about RNN like LSTMs and GRU being used, but more recently, transformers have become dominant because they work so much faster and handle longer sentences with ease. Okay, let's talk about how AI can actually write. We're focusing on language generation models. These are the engines behind things like chatbots and content creation. The key ingredient here is often the transformer architecture, which lets the model understand relationships between words in a whole sentence at once. Think of it as having a much better memory for context than older systems. Some really popular examples include the GPT series from OpenAI, LaMDA from Google, and POT-LM2. They've all been trained on huge amounts of text and code to learn how language works, and it's what makes them so good at generating human-like responses. Okay, let's talk about how we actually talk to these powerful AI models. Prompt engineering is all about designing the perfect instructions of prompts to get the best results from LLM like GPT. It's not just asking a question, it's carefully shaping your request. We can start with zero-shot prompting, which is giving the model a task without showing any examples. Then there's few-shot prompting, where we provide a couple of good examples to show it what kind of response we're looking for. And finally, chain-of-thought prompting. This is really powerful. It encourages the model to actually think out loud and explain its reasoning process step by step. Think of it like teaching the AI how you would approach a problem yourself. A good prompt structure helps the LLM understand exactly what we want, leading to much more relevant and accurate responses. Okay, let's talk about two really cool approaches that help AI tackle new challenges with less data: zero-shot and few-shot learning. Traditionally, you'd need tons of examples for a model to understand something completely new. But zero-shot means the model can recognize things it's never seen before simply by understanding how those things relate to what it already knows. Think of it like this: if a model has learned what a horse is, and a zebra shares similar characteristics, it might be able to figure out what a zebra is without ever having been shown one. Few-shot learning takes it a step further. We give the model just a handful of examples, maybe 5 or 6, and it can quickly adapt to a new task. It's like teaching someone a new skill really fast with just a quick demonstration. Okay, so let's talk about how computers can actually understand what we're asking for. Traditionally, searching was all about matching words exactly like a simple keyword hunt. But modern search is much smarter. It uses something called semantic search. Instead of just looking for the words you type, it tries to figure out what you mean. It's powered by NLP, which stands for natural language processing. Techniques like word embeddings help computers see relationships between words. Similar words are close together in a mathematical space. We also use things like knowledge graphs that connect different concepts and entities. Finally, sentence embeddings allow the system to understand entire sentences. Basically, it converts your query into a numerical representation of its meaning, then compares this with the meanings of everything else available, leading to more relevant results than just matching keywords. Okay, let's talk about how we measure text similarity. It's a really important concept in NLP. We use different ways to figure out just how alike two pieces of writing are. One popular method is cosine similarity. Think of each document as a point in space, and the closer those points are, the smaller the angle between them, the more similar they are. Then there's the Jaccard index, which focuses on comparing sets of words. Basically, how much do they share? Finally, we have Levenshtein distance, also known as edit distance. This counts up all the changes you need to make to one string to turn it into another. So, depending on what you're looking for, there's a technique that suits the task. Okay, let's talk about how we get our text ready for computers to understand. It's like cleaning up a messy room before you start organizing. The first step is often tokenization, basically splitting the text into individual words or phrases. Then, we usually lowercase everything so that they are treated as the same word. Next, we remove common stop words like the a and is, because they don't really add much to the meaning. Finally, we use stemming or lemmatization, which tries to get all variations of a word down to its root form. Think of it like finding the core of each word. Let's talk about text-to-speech. It's a really fascinating area of AI. Basically, TTS systems take written words and turn them into spoken audio. The process starts with converting the text into phonemes, which are like the building blocks of sound. Then, an acoustic model figures out how those sounds should be produced. Finally, a vocoder uses this information to create a realistic-sounding waveform. There are different approaches. Older systems use pre-recorded snippets, while newer neural TTS models use powerful AI algorithms that have really upped the quality and naturalness of speech. Think of it as teaching a computer to mimic how humans talk. Let's talk about speech-to-text, or ASR. Basically, it's how computers understand what we say. Think of Siri or Alexa. They use ASR to convert your voice into text. Traditionally, systems use things like hidden Markov models, but now deep learning is the main game changer. RNN and LSTMs are really good at handling the way speech varies, and transformers are taking over too. The process involves turning sound waves into numbers, acoustic features, training a model to link those numbers to sounds, and then finally decoding that audio to get the most likely words. Okay, let's talk about natural language inference. Essentially, it's all about figuring out if one sentence logically follows from another. Think of it like a detective. We have a premise, which is our starting clue, and a hypothesis, the thing we're trying to prove or disprove based on that clue. The model has to decide if the hypothesis is true, entailment, false contradiction, or just, unclear and neutral. Powerful models like BERT have really revolutionized this area, allowing us to understand context in a way that was previously impossible. This ability is incredibly useful for things like building smarter chatbots, answering questions more accurately, and even improving how we summarize text. Okay, let's talk about intent detection and slot filling, a really crucial part of how AI understands us. Basically, it's all about figuring out what the user actually wants to do and pulling out the specific details they need to make that happen. We use machine learning models, often based on things like transformers, to predict the intent, like order pizza or book a flight. Then we look for key pieces of information. Those are the slots, like the destination city or the date you want to travel. It's like a little puzzle where we piece together the user's request. Okay, so let's talk about entity linking and disambiguation. It's a surprisingly important step in making AI truly understand what we're talking about. Basically, we want our machines to know that Apple the fruit is different from Apple the company. It's like teaching them to differentiate between similar-sounding words or names. This process takes mentions of entities, things like people, places, or organizations, and connects them to a unique ID in a big database, like Wikipedia or something similar. And crucially, it solves any confusion, making sure we're always referring to the right entity. Without this, AI struggles with tasks like answering questions or summarizing text effectively. Let's talk about a really important part of understanding text. It's called coreference resolution. Basically, it's like training an AI to figure out which words or phrases are talking about the asterisk. Same thing, asterisk. Think of pronouns like he, she, it, and even groups of words that refer to the same person or object. Early systems used complicated rules, but now powerful language models, especially things like BERT, have made this process incredibly accurate by learning from tons of text data. It's a surprisingly tricky problem, but coreference resolution is key to making AI truly understand what we're reading. Okay, let's dive into word sense disambiguation, or WSD for short. Basically, it's the process of figuring out which meaning a word has in a specific sentence. Think about words like bank. Does it mean a financial institution, or the side of a river? WSD helps computers understand that nuance. It's super important because if a computer misinterprets a word's meaning, everything downstream, like understanding the sentiment of a review or translating a document accurately, can go wrong. We'll look at some different approaches to solving this problem, from simple rules based on dictionaries to more complex machine learning models that learn from labeled data, and even leveraging external knowledge bases. Okay, so let's start with the foundational step: text mining and information extraction. Basically, we're taking this massive amount of unstructured text data, stuff like news articles or social media posts, and trying to pull out useful insights. It starts with breaking down that text into smaller pieces, like individual words. Then, we use techniques like stemming and lemmatization to clean up those words, making sure they're consistent. We also remove common stop words that don't really add much value. But the real power comes from information extraction, things like identifying people, organizations, or locations in a text, and even figuring out how these different elements are connected to each other. For example, we can recognize that Elon Musk works at Tesla. It's all about turning the raw data into something computers can actually use. Okay, let's talk about text augmentation. It's a really smart way to push your NLP models. Basically, we want our models to see lots of different ways to say the same thing, so they don't just memorize specific examples. We do this by creating slightly altered versions of our existing training data. Think synonyms for words, inserting new terms randomly, or even translating and then retranslating the text. It's a simple idea that can have a big impact on how well your model performs in real-world situations. Just make sure you're doing it in a way that keeps the overall meaning of the text intact. Okay, let's dive into a slightly darker side of NLP: adversarial attacks. Basically, someone can create tiny changes to text that are practically invisible to us, but they completely throw off an NLP model. It's like a clever trick. These attackers craft subtle alterations to sentences, exploiting weaknesses in how these models make decisions. For example, adding just one or two words can dramatically shift sentiment analysis, turning a positive review into a negative one. There are different types of attacks, from quick and easy methods like FGSM to more complex iterative approaches. And then there are black box attacks, where the attacker doesn't even need to know how the model works, they just keep trying until something goes wrong. Okay, let's talk about explainability in NLP. Large language models are incredibly effective at what they do: writing, translating, answering questions, but it can be hard to understand why they make the decisions they do. It's like a black box. Understanding why a model is making a prediction is really important for building trust, finding and fixing errors, and even making sure we're complying with regulations in industries where transparency matters. We have several techniques we can use. Attention mechanisms let us see what parts of the input the model focused on. Lime and SHAP help to explain how specific features contribute to the output. This is an area of ongoing research, so expect to see even more sophisticated methods emerge. Okay, let's talk about ethics in the world of natural language processing. Think about how powerful these tools are. They can understand and generate human language like never before. But that power comes with responsibility. One of the biggest issues is bias. NLP models learn from data, and if the data reflects existing prejudices in society, whether it's related to gender, race, or anything else, the model will likely amplify those biases too. It can show up in things like hiring processes or even loan applications. Privacy is another major concern. We're feeding massive amounts of personal text into these systems, so protecting that information is absolutely vital. And then there's the potential for misuse. NLP can be used to create incredibly convincing fake news or propaganda, which is a real problem for society. Finally, because many of these models are complex black boxes, it's often hard to figure out why they make certain decisions, and that lack of transparency makes it difficult to hold them accountable. The good news is, researchers and developers are working on solutions, like using diverse datasets and exploring techniques that make NLP more understandable, but it's an ongoing effort. Okay, let's talk about a really important aspect of AI fairness. Large language models are amazing at generating text and understanding language, but they're only as good as the data they learn from. And unfortunately, that data often contains existing biases in society. These biases can creep into the model itself, leading to outputs that perpetuate stereotypes or discriminate against certain groups. It's not about intentional badness, it's a reflection of the world as it is currently represented in the training information. We need to understand where these biases come from, whether it's skewed data collection, issues with how the algorithms are built, or simply uneven representation, and then actively work on solutions like adding more diverse data, developing tools to detect bias, and even changing the way we train the models themselves to be fairer. Let's talk about a really important area within NLP: low-resource languages. Think about languages spoken by smaller communities around the world. These languages often don't have as much digital text or speech available online, which makes it tough to build powerful NLP models using standard approaches. The biggest hurdles are simply having enough data to train those models effectively, and also ensuring that the model doesn't just memorize what it does *C. We're seeing some exciting solutions though, like taking models already trained on languages with lots of data transfer learning and adapting them. Another useful strategy is creating shared embedding spaces, so words from different languages can be understood relative to each other. And then there's clever data augmentation techniques, where we generate new training examples automatically. It's a fascinating area of research that's helping to democratize access to NLP technologies for more people. Okay, so let's dive into multilingual NLP, essentially teaching computers to understand text in many different languages. For a long time, getting good results with non-English text was really tough. We've made huge strides though. Machine translation is now mostly powered by clever neural networks like transformers. But it goes deeper than just translating word for word. We also use techniques that create shared representations of meaning across languages called cross-lingual embeddings. These help models understand concepts even if they're expressed differently in each language. And the really exciting part, we can now get surprisingly good translations with very little specific training, zero-shot and few-shot translation. It's all thanks to massive multilingual pre-trained models. Of course, there are still challenges like handling mixed languages within a sentence and making sure translations accurately reflect cultural context. Okay, so let's dive into cross-lingual transfer learning. Basically, we're taking a really smart model that's already been trained on tons of data in one language, usually English, and then adapting it to work well with another language, even if there isn't as much data available for that new language. We can do this by fine-tuning the whole model or using smaller adapter modules. Models like BERT and XLM-ROBERT are frequently used as the foundation for these techniques. They've already learned a lot about language structure, so we just need to tweak them slightly to fit the specific nuances of the new language. Okay, let's talk about how we actually measure the progress of NLP models. It's not enough just to build something that looks impressive. We need a way to see if it's truly good at what it's supposed to do. That's where benchmark datasets come in. Think of them as standardized tests for AI. We use specific, curated collections of text data like news articles, movie reviews, or even questions and answers to evaluate how well models perform on tasks like classifying text, answering questions, or translating languages. These datasets let us compare different NLP approaches and track advancements over time. There are a few broad categories: text classification, where we're testing how well the model categorizes text; question answering, where the AI needs to understand context and find answers; machine translation, which tests its ability to translate between languages; and named entity recognition, which focuses on identifying key things like people or organizations within text. And just a quick note, it's really important to be aware of potential biases in these datasets because they can unintentionally influence what models learn. Okay, so after we build our NLP models, we need to figure out how good they actually are. It's not enough just to say it works. We use different metrics depending on the task. Accuracy is a quick and easy measure. It tells us what percentage of times the model gets things right. But precision and recall give us more detail about where the model might be failing, like if it misses important positives or incorrectly identifies many negatives. The fun score balances these two, and then we have task-specific metrics like blue for translation, which looks at how similar the machine's output is to human translations, or rouge for summarization, looking at overlap between generated summaries and what a good summary should look like. Perplexity helps us understand how confident our language model is in its predictions. Lower is generally better. Okay, so let's talk about transformers. They've completely changed the game when it comes to creating text. Instead of processing words one at a time like older models, transformers look at the whole sentence all at once. This is thanks to something called self-attention, which basically helps the model understand how important each word is in relation to every other word. Think about it like reading a paragraph. You don't just read the first sentence and then the second. You're constantly connecting ideas together. Transformers have an encoder, which figures out the context of your input, and a decoder that uses that context to generate new text. A really important thing is positional encoding, because these models don't inherently understand order. We add information about where each word is located in the sequence. Models like GPT are built using this architecture, and they're incredibly powerful from writing articles to translating languages. Okay, let's talk about how we take these massive language models and really make them our own. Think of LLM like GPT-3. They've read pretty much everything on the internet. But that means their knowledge is super general. Fine-tuning is all about taking that existing foundation and teaching it something very specific. We do this by training it on a smaller, more targeted data set. There are different ways to approach this. You can update the model's parameters, which takes a lot of resources, or we can use techniques like low RA, which only tweaks a tiny portion of the model and saves us a ton of time and power. Getting your data right is absolutely key. It needs to be clean, relevant, and formatted in a way that makes sense for the model. And thankfully, tools like Hugging Face transformers make this whole process much easier. Okay, let's talk about prompt tuning and adapters. Really cool ways to make large language models even better at specific tasks. Basically, we're finding clever ways to guide these massive models without having to completely retrain them. Prompt tuning involves adding tiny, trainable vectors like little hints to the model's understanding of words. It's super efficient because it only tweaks a small part of the model. Adapters, on the other hand, are like mini networks that get plugged into the LLM. They learn specific skills and act as shortcuts for new knowledge. They offer more flexibility than prompt tuning. Think of them as adding specialized modules. We'll look at some key differences between the two approaches to help you understand which might be best for your project. Okay, let's talk about knowledge distillation, a really smart way to make huge language models more manageable. Think of it like this: you have this massive, incredibly capable teacher model, maybe GPT-3 or LM, but running it can be super expensive. Distillation lets us take what that teacher has learned and transfer some of that wisdom to a smaller student model. The student isn't just trying to guess the right answer directly, instead, it's learning how the teacher would approach the problem, mimicking its output probabilities, essentially learning to think like the big guy. We use soft labels from the teacher, which are basically a probability distribution for each possible outcome, and train the student to match those distributions. A temperature parameter helps us control how smooth or focused these probabilities are, allowing the student to pick up on more nuanced relationships. The result? A smaller model that still performs remarkably well, faster, cheaper, and easier to use. Okay, so let's think about how conversational AI actually works. It's not just magic. It all starts with the user input their message to your chatbot or voice assistant. First, we need to clean that up and prepare it. This involves breaking the text down into smaller pieces, simplifying words, and getting rid of unnecessary ones. Then comes natural language understanding, which is where the AI tries to figure out what the user actually wants. It's like figuring out their intent. Are they asking a question, making a request, or just saying hello? After that, we have dialogue management. This part keeps track of everything that's happened in the conversation so far and decides what the next step should be. Finally, it generates a response, whether that's pulling information from a database, crafting a helpful answer, or even triggering something else entirely. Okay, so we're shifting gears a bit and looking at how knowledge graphs are making NLP even smarter. Basically, instead of just seeing words in isolation, we're building a map that shows how things relate to each other. Imagine it like a really detailed mind map. Nodes represent the things themselves, like people or ideas, and edges show how they connect. For example, Albert Einstein is connected to theory of relativity with an edge labeled developed. This graph structure allows NLP systems to actually understand what's being asked or discussed, leading to huge improvements in question answering, recommendations, and even summarization. It adds a layer of context and reasoning that was previously missing. Okay, let's talk about how we can boost our NLP systems by blending the best of both worlds: neural networks and symbolic reasoning. Basically, we're giving these models a brain that understands why something is happening, not just recognizing patterns. We have a neural network part, which is really good at seeing and learning from data like sentences. Then we add in a knowledge base, like a giant collection of facts, and we'll think of it as common sense. The trick is figuring out how to get these two parts to work together smoothly, often using techniques like attention, so the neural network can focus on the most relevant information from the knowledge base. This approach helps with things like answering complex questions and understanding situations that require reasoning beyond just recognizing words. Let's kick things off with computer vision. It's essentially teaching computers to understand what they're seeing, just like we do. Think about it: recognizing a cat in a photo, finding all the cars on a street, or even breaking down an image into different parts. Early approaches involved manually designing features like edges and corners, but modern CV is much more sophisticated, using complex algorithms and models. Okay, so let's kick things off with image processing. It's really the groundwork we need before diving into NLP or computer vision. Basically, it's about taking raw images and making them easier to work with. We start by cleaning up the data, getting rid of noise and adjusting contrast. Then, we extract key features like edges and textures that are important for recognizing objects. Think of it like preparing a canvas before you paint. We use techniques like converting an image to grayscale or applying thresholds to separate foreground from background. Image processing provides the initial information computer vision models need. Okay, let's talk about how we can make images look their absolute best before feeding them to our AI systems. Image enhancement is surprisingly important. We're looking at things like reducing noise, think of that grainy look on all photos, and sharpening details. Contrast adjustment helps balance out the brightness so everything pops. And sometimes we need to remove blur from motion like a photo taken while moving. These techniques are often built right into our AI models, making them more robust and reliable. Okay, let's talk about image segmentation. Basically, it's how computers learn to see distinct objects within a picture, not just identify there's something there, but actually pinpointing exactly where it is and labeling what it is. We have different approaches. Semantic segmentation labels every pixel with the object class, like coloring all the cars blue. Then we can go even further with instance segmentation to distinguish between individual objects of the same type, so recognizing each car separately, not just a blob of cars. There are simpler methods like thresholding, where you pick a brightness value and group pixels that match it, and more advanced techniques using things like UNet architectures, which are really powerful for medical imaging. Segmentation is a core building block for tons of cool applications, from self-driving cars to analyzing scans in medicine. Okay, let's talk about edge detection. It's a really crucial step in computer vision. Essentially, we want to find where things change drastically within an image. Those are our edges. Now, there aren't just one or two ways to do this. The Canny detector is often considered the top choice because it does a really thorough job of filtering out noise and finding clean edges. It's like a multi-step process, moving the image first, then figuring out where the changes are happening, thinning those edges out so they're nice and sharp, and finally making sure we only keep the truly important ones. Then you have the Sobel operator, which is simpler but still quite effective, and Pruitt too. Finally, there's the Laplacian of Gaussian. It combines blurring with a way to find these change points effectively. Choosing the best one really depends on what you're trying to do with the image and how much processing power you have available. Okay, so let's jump right into image classification. Basically, we're teaching computers to look at pictures and tell us what they see. We start by collecting lots of images, say, of cats and dogs, and labeling each one correctly. Then, we use a model, often a convolutional neural network or CNN, which is really good at finding patterns in pixel data. The CNN learns from these labeled examples, adjusting itself until it can accurately identify the objects in new pictures it's never seen before. It's like teaching a child to recognize animals. You show them lots of examples and eventually they get it. Okay, let's talk about object detection, a really important part of how AI sees the world. Basically, it's not just recognizing there's a cat in a picture, but pinpointing exactly where that cat is with a box around it. There are two main ways to tackle this: one-stage and two-stage detectors. One-stage methods like YOLO are super fast because they predict everything at once, bounding boxes and class labels directly from the image. Two-stage approaches first find potential areas of interest, then classify them. Models like faster CNN and SSD are popular choices. Each has its strengths in terms of speed and accuracy. Okay, let's talk about YOLO. It's a really clever approach to object detection. Basically, instead of looking at an image piece by piece, YOLO takes the entire picture in one go and tries to figure out what's in it, where everything is, and what it is. It does this by dividing the image into a grid and predicting bounding boxes for objects directly from that grid. And because it only needs to look once, it's incredibly fast, making it perfect for real-time applications like self-driving cars or security cameras. It's surprisingly accurate too, and its relatively simple design makes it a really popular choice in the world of computer vision. Okay, let's dive into SSD's single-shot detector. Think of it as a super speedy way to find objects in an image. Instead of first searching for potential areas and then classifying them, SSD directly predicts where the objects are and what they are, all within one pass through a single neural network. It's brilliant because it's much faster than some other methods, especially when you need real-time detection, like in self-driving cars or video surveillance. Okay, let's dive into faster RCNN. It's a really clever system for finding objects and images. Essentially, it works in 2 steps. First, an RPN, think of it like a map maker, scans the image and suggests potential areas where objects might be hiding. Then, it takes those proposed regions and uses them as a starting point to classify what's inside each area and accurately draw boxes around them. It's designed to do all this efficiently, making object detection much faster than older techniques. Okay, let's talk about semantic segmentation. It's a really cool step in the world of computer vision. Basically, instead of just drawing boxes around objects like car or person, it labels asterisk every single pixel asterisk in an image with what it is. So, if you have an image of a street scene, every brick would be identified as brick, every patch of grass as grass, and so on. It's like creating a detailed, color-coded map of the entire picture. We use things like FCN and UNets to achieve this, and models like MaskRCNN can even predict both where objects are asterisk and asterisk, how they're segmented at the same time. You see it in all sorts of applications: self-driving cars understanding the road surface, doctors using it for precise diagnosis in medical scans, or even analyzing satellite images to track changes in land use. Okay, let's talk about instance segmentation. It's a really important technique in AI because it allows us to go beyond just recognizing asterisk what asterisk objects are in an image, like saying there's a car. Instead, it tells us asterisk how many asterisk of each object there are and exactly where they are, even if they overlap or are partially hidden. It's like drawing precise outlines around each individual instance. Models like MaskRCNN and YOLOVate use powerful CNN combined with clever attention mechanisms to make this possible. Okay, let's talk about keypoint detection. It's a really important step in getting computers to see and understand images. Basically, it's like giving the computer a set of landmarks or points that are distinctive within an image. There are several techniques we can use, from classic methods like iris corner detection, which finds corners based on intensity changes, to edge detection using canny, and more advanced ones like SIF, which is incredibly robust to changes in scale and rotation. These keypoints become really valuable because they provide a structured way for computers to analyze images. It's not just about seeing pixels anymore, it's about recognizing patterns and shapes. And you'll find that keypoint detection gets used in tons of applications, like identifying objects in pictures, finding similar images based on their features, or even figuring out how someone is standing or moving. Okay, let's dive into face detection and recognition. Basically, we're teaching computers to spot faces in pictures and videos. That's the first part. Then, if it finds a face, it tries to figure out asterisk who asterisk it is. It does this by looking for specific patterns or features that are unique to each person. Algorithms like Cascades and HRG help find these facial characteristics. Once a face is detected, a trained model, often a type of neural network, compares those patterns against what it's learned from tons of examples. This allows the system to match a new face to an existing identity. You'll see this used everywhere, from security systems and social media tagging, all the way through access control and even biometric authentication. Let's talk about OCR, optical character recognition. Basically, it's how computers learn to read text from images, like a scanned document or a photo of a sign. First, the image gets cleaned up and made more readable. Then, it's broken down into individual characters. The computer analyzes these characters, looking for important features like lines and curves. Finally, a smart model figures out what each character is. Think of it like matching clues to solve a puzzle. OCR has tons of uses, from digitizing old documents to helping people with vision impairments. Okay, let's dive into convolutional neural networks, or CNNs. These are a really important part of computer vision and are what allow computers to see. Think of them like a visual detective. They look for patterns in images, starting with simple things like edges and corners, then building up to recognize more complex objects like faces or cars. The magic is in these layers called convolutional layers, which basically slide filters across the image, searching for those key features. and pooling layers help reduce the size of the data so the network can learn effectively. It's a pretty clever system, and they're responsible for much of what we see computers doing with images today. Okay, so let's zoom in on CNN architectures. These are essentially how we teach computers to see images. We started with LaNet back in '98, which was a really early attempt at recognizing handwritten digits. Then came AlexNet in 2012. This is the model that really kicked off the deep learning revolution in computer vision. It used a lot more layers and benefited massively from training on huge datasets. VGG models followed with their simple, uniform design, making them very popular for transfer learning. And finally, ResNet in 2015 introduced a clever trick: residual connections that allowed us to build much deeper networks without running into problems with vanishing gradients. It's like giving the network shortcuts to help it learn effectively. Okay, so let's talk about transfer learning in computer vision. Basically, instead of building a completely new image recognition model from scratch, which can be really resource intensive, we start with something that's already learned a lot. There are models like ImageNet that have been trained on billions of images, and they've picked up on the basic visual elements, edges, textures, shapes, really fundamental things. We can take one of these pre-trained models and then adapt it to our specific problem by training just a few more layers with our own data. It's like giving an experienced artist a head start. They don't have to learn everything from zero. Okay, let's talk about vision transformers, or VTS. They are a really exciting development in computer vision. Basically, they take the innovative transformer architecture, which was originally designed for natural language processing, and apply it to images. Instead of using traditional convolutional neural networks, VTS treat an image as a sequence of patches. Think of them like individual words in a sentence. They then embed these patches into vectors, add positional information so the model knows where each patch is located, and finally feed everything through a standard transformer encoder. This allows the model to really grasp the global context within an image. It's able to see how different parts of the image relate to each other in a more nuanced way than older methods. And because transformers scale so well, VTS have become incredibly powerful when trained on massive data sets. Okay, let's talk about attention in computer vision. For a long time, CNN treated every part of an image as equally important, but that's not always realistic. Think about it: a cat in the snow gets processed differently than a cat on a beach. Attention mechanisms solve this problem by allowing the model to actively focus on what's most relevant for each task. It's kind of like how we look at things. We don't just stare at everything equally, right? They use something called a QKV architecture. It generates a query, compares it to keys and values, calculating attention weights that tell the model where to really concentrate its efforts. This leads to better accuracy, handles complex scenes much more effectively, and even allows us to see why the model is making certain decisions. Okay, let's talk about object tracking. It's really important for a lot of AI systems. Basically, we want our computers to be able to follow objects as they move through video or images. There are several ways to do this. One common method is called Kalman filtering, which uses predictions and measurements to estimate where an object should be. Then there are correlation filters, which learn how to respond specifically to the target object. And more recently, deep learning techniques like Siam Mask and Deep Salt have become incredibly popular because they're really good at handling situations where objects might get hidden or change their appearance. Okay, so let's talk about how AI can actually see videos. It's a really exciting area. We're focusing on techniques like object detection, basically teaching the computer to spot things like cars or people in each frame of the video. Then there's action recognition, which is all about figuring out what's happening. Are they walking? Are they running? Different models are used for these tasks, from 3D CNN that treat a video like a three-dimensional volume to transformer-based approaches that can understand the bigger picture and relationships within the footage. And of course, this technology has some incredible applications, everything from improving security systems to helping self-driving cars make smarter decisions, and even automating content moderation online. Okay, let's talk about 3D object detection. It's a really cool advancement in computer vision. Basically, instead of just finding objects asterisk and image like we do with regular object recognition, we want to know where they are and what their shape is in 3D space. This often involves using sensors like LiDAR or stereo cameras that give us depth information alongside the standard color images. The raw data gets transformed into a point cloud. Think of it like a giant collection of points representing the object's surface. Then, we use specialized neural networks, like PointNet, to analyze this point cloud and figure out where these objects are and how they are oriented in 3D. It's being used everywhere from self-driving cars to robots and even augmented reality, really opening up possibilities for understanding our surroundings. Okay, let's talk about scene understanding. Think of it as teaching a computer to see and truly understand what's going on in an image or video. It's more than just recognizing individual objects like a car or person. It's about figuring out how those objects relate to each other, like that car is parked next to that building. We use techniques like object detection and recognition to spot things, scene graphs to map out relationships, and semantic segmentation to label everything. Convolutional neural networks are the workhorses for a lot of this, but graph neural networks and even transformers are playing an increasingly important role. Ultimately, all of this helps us build systems that can navigate complex environments and make intelligent decisions. Okay, let's talk about image captioning. It's all about teaching computers to understand pictures and then tell us what they see in words. We start with convolutional neural networks, CNNs, which are really good at finding patterns and features within an image, like objects or textures. Then recurrent neural networks, specifically LSTMs, come into play to string those descriptions together sentence by sentence. And the key ingredient? Attention. It's what allows the model to focus on exactly what's important in the picture when it's building its description. There are some really famous models like Show, Attend, and Tell, which was a groundbreaking development, and now we're seeing transformer-based approaches becoming dominant. They're incredibly powerful at understanding complex relationships within images. Okay, let's talk about GAN. They are a really fascinating concept in AI. They work like a clever competition between two neural networks. You have a generator, which is basically trying to create something new that looks like it belongs to an existing dataset, almost like a forger making counterfeit money. Then you have a discriminator, which is the detective. Its job is to figure out whether what the generator creates is real or fake. They constantly challenge each other, and through this ongoing battle, both networks get better and better until the generator can produce incredibly realistic results. Think about creating new images, changing the style of an existing picture, or even generating music. GAN are being used for all sorts of cool things. Let's dive into style transfer. It's basically about taking the content of one image and applying the look and feel of another. The original technique, neural style transfer, was a breakthrough, using deep learning to extract what makes an image contentful and what makes it have a particular style. We then minimize the difference between those two things. Newer methods like adaptive instance normalization are much faster for real-time applications, and CycleGAN lets us transfer styles between completely different types of images. Imagine turning a photo into a painting or vice versa. It's all about blending the best of both worlds. Okay, let's dive into image super resolution, essentially making blurry images sharper. It's a really useful technique with tons of applications, from restoring old family photos to improving medical scans. There are several approaches. Traditionally, we use things like bicubic or Lanczos interpolation, which are fast but can lead to blurriness because they just guess what pixels should be based on their neighbors. Then came SRCNN, a clever convolutional neural network that learned how to upscale images directly. More recently, SGAN and Real SGAN have really stepped up the game, using generative adversarial networks (GAN) to create much more realistic and detailed results. They're better at adding details that weren't actually in the original image. It's important to remember that there are always trade-offs. Faster methods might not be as detailed, and higher quality can sometimes require more processing power. Okay, let's talk about getting rid of the fuzz in images. We call that image denoising. It's a really important step before you do anything else with an image. There are a few different ways to tackle this problem. The simplest is using linear filters, which basically blur the image by averaging pixels together. Then there's the median filter, which is great for removing salt and pepper noise, those random white or black speckles. And finally, wavelet denoising breaks the image down into its different frequency components, letting you remove the noise without blurring out important details. Okay, let's dive into pose estimation. Basically, it's about figuring out where the important parts of a body are in an image. Think elbows, knees, wrists, all those joints. This is super useful because it lets computers understand what people are doing and how they're moving. It opens doors to really cool things like controlling devices with gestures or creating more believable avatars in VR. There have been some great advancements. We've gone from older methods using convolutions to now sophisticated networks like stacked eyeglasses, which are really good at seeing the bigger picture, and libraries like OpenPose that make it relatively easy to get started. Okay, let's talk about hand gesture recognition. It's a really interesting intersection of NLP and computer vision. The problem is that computers traditionally find it hard to recognize hands. They vary so much. But when we combine these two fields, things get way better. We use CNN to analyze the images of our hands and extract important features. Then recurrent neural networks help us understand the asterisk sequence of movements, because gestures often happen in a specific order. Models like MobileNet V2 with LSTMs are commonly used for this task. Ultimately, hand gesture recognition is powering some really cool things, from controlling your smart home to creating more intuitive gaming experiences and even helping people who use sign language. Okay, let's talk about facial expression analysis. It's a really fascinating intersection of computer vision and AI, basically teaching machines to read our emotions from our faces. First, we use cameras to capture images or videos. Then the system finds those faces within the image and makes sure they're properly aligned for accurate analysis. Next, it identifies key landmarks like the corners of your eyes and mouth, creating a geometric map of your face. This data is fed into trained models, typically deep learning networks like CNN, that have learned to recognize different emotions based on massive amounts of labeled facial expressions. Finally, the model predicts what emotion you're showing. It's used in tons of places, from analyzing customer sentiment and monitoring patients for mental health conditions to making robots more intuitive and even improving security systems. Let's talk about how we're using NLP and computer vision together to revolutionize medical imaging. Think about all the incredible amounts of data in X-rays, MRIs, and CT scans. It's a massive challenge for doctors to keep up with. The good news is that by combining these technologies, we can automate parts of the analysis process. Computer vision helps us pinpoint specific areas of interest within an image, like tumors or fractures. Then NLP steps in to read radiology reports, pulling out key information and connecting it to those visual findings. This collaboration leads to more accurate diagnosis and even automated report generation, freeing up radiologists' time for what they do best: patient care. Okay, let's talk about anomaly detection with images. Essentially, we're looking for things that don't belong, pixels, parts of pictures, or even entire images that are noticeably different from what we expect to see. It's super useful in all sorts of places, like spotting fraudulent ID, finding tumors in medical scans, making sure products are made correctly on a factory line, and even keeping an eye out for unusual activity in security footage. We use techniques like autoencoders, which are trained on normal images, so anything that looks wildly different will have a big error when it tries to recreate itself for one class SVM, which learn the boundaries of what's considered normal and flag anything outside those bounds. And then there's isolation forest, which is a clever way to spot anomalies by randomly breaking down the data. Okay, let's talk about self-supervised learning in computer vision. It's a really exciting area because it tackles a huge problem we have in CV, getting massive amounts of labeled data. Instead of relying on humans to painstakingly tag every image, SSL uses the images themselves to teach the model. Basically, we create artificial pseudo-labels by transforming the images, like rotating them or cropping them out, and then train the model to figure out how to undo those transformations. It's learning about what makes an image asterisk an asterisk image, not just memorizing specific examples. Models like SimCLR and ME are really making waves in this space, showing that you can get incredibly powerful representations with a lot less human effort. Okay, let's talk about contrastive learning in the context of computer vision. Essentially, it's a clever way to teach computers how to understand images better by comparing them. Imagine you have two slightly different shots of the same cat. We treat those as positive pairs. Contrastive learning then tries to make the computer recognize these images as related, creating close proximity in its image understanding space. It does this by also looking at images that are similar, like a picture of a dog, and pushing them further apart. Models like SimCLR, MoCo, and Bio have really made a splash using this technique to learn powerful image representations. Okay, let's talk about a really fascinating and slightly unsettling aspect of computer vision. We've seen incredible progress with AI recognizing images, but it turns out these models can be tricked pretty easily. We call this adversarial attacks. Basically, someone creates an image that looks almost identical to a real one, but has tiny, carefully designed changes like just a few pixels that cause the model to misclassify it completely. It's like a clever trick. There are several methods for generating these attacks, FGSM and PGD being two of the most common. They are all about finding those subtle nudges that throw off the AI. And because of this vulnerability, it's important to think about how we can make computer vision systems more robust and secure, especially in areas like self-driving cars or medical diagnosis. Okay, let's talk about explainable AI, or XAI, specifically within the world of computer vision. These deep learning models are amazing at spotting things in images, cats, cars, faces, but they often do it without us really knowing how they arrive at those conclusions. It's like a black box. XAI is all about opening that box up and figuring out what's going on inside. We have techniques like LIME, which looks at how changing the image slightly affects the prediction. CHAP uses some game theory to understand which features were most important, and GradCAM highlights specific areas in an image that led to a particular decision. Essentially, XAI helps us build trust and make sure these systems are fair and reliable. Okay, let's talk about a really important aspect of computer vision: fairness. These models are trained on massive datasets, and if those datasets aren't representative, the models can inherit and even amplify existing biases in society. It's not just about technical accuracy, it's crucial that these systems treat everyone equally. We need to look at where bias comes from, whether it's a lack of diversity in the data itself or unintentional bias during the design process. You'll hear examples like facial recognition struggling with darker skin tones, or difficulty identifying pedestrians from certain groups. The good news is that there are steps we can take to mitigate these issues. Careful data collection and ongoing monitoring are key. Okay, so let's talk about multi-camera systems. It's a really powerful technique in the world of AI. Basically, instead of just relying on one camera's view, we use several cameras to get a much broader understanding of what's happening. This is especially useful for things like robots and self-driving cars. They need to see everything around them. We combine information from all those cameras using something called sensor fusion, which helps us estimate depth really well. And when it comes to tracking objects, it becomes way easier because we can follow them as they move between different camera views. Okay, let's talk about depth estimation and stereo vision. These are key technologies that allow computers to see how far away things are in the real world. Think of it like having two eyes. By comparing what each eye sees, we instantly get a sense of depth. Stereo vision uses two cameras to mimic this process, finding differences between the images they capture. We use techniques like block matching, which is pretty straightforward, basically looking for pixels that line up in both pictures and using that to figure out how far away things are. Then there's structured light, where we shine patterns onto objects and measure how those patterns change, and photometric stereo, which uses light reflection to map the 3D shape. Okay, let's talk about structure from motion, or SFM. It's a really cool technique that lets us build 3D models from regular photos. Basically, it's like detective work for cameras. We start by finding distinctive points, called features, in each image, think corners or edges. Then, we match those features across different pictures. Using the camera angles and these matching points, we calculate where those features actually are in 3D space. Finally, we refine everything to make sure it all fits together perfectly. It's a core part of how things like photogrammetry, creating 3D models from photos, work. And it's closely linked with technologies like SLAM and multi-view geometry. Let's talk about photogrammetry. Basically, it's a way to build 3D models using just photos. Imagine taking lots of pictures of an object from different angles, like a building or even a dinosaur skeleton. The software then analyzes these overlapping images, finds common points, and uses that information to reconstruct a detailed 3D representation. It's commonly used in fields like archaeology, surveying, and robotics because it allows us to capture the real world digitally without needing specialized equipment. Structure from motion and multi-view stereo are two main techniques used. Think of SFM as figuring out where the cameras were when they took each picture, while MVS then fills in all the details. Okay, so let's talk about building 3D models from pictures. Pretty cool stuff. Basically, we take a bunch of photos of an object from different angles and use some clever algorithms to stitch them together. We're talking about something called structure from motion, or SFM, which figures out where the camera was when each photo was taken. Then, multi-view stereo, or MVS, uses that information to create a 3D point cloud. Think of it like a really detailed map of the object's surface. From this cloud, we can then generate a mesh, creating a smooth, polygonal model you could actually use in VR or AR. And get this, newer techniques like neural radiance fields are using AI to create even more realistic 3D representations, although they need some serious computing power. It's finding tons of applications from virtual worlds and robots to preserving historical landmarks. Okay, let's talk about SLAM. Imagine a robot exploring a new building. It doesn't have a GPS. SLAM is how it figures out where it is and what's around it, asterisk at the same time, asterisk. It uses sensors like LiDAR and cameras to build a map as it goes, constantly updating its location within that map. A key part of SLAM is loop closure, basically, realizing when it's back somewhere it has been before, which helps correct any errors and make its map really accurate. Let's talk about how AR and computer vision work together to create these amazing experiences. Basically, your device uses its camera to see the world around it, just like we do. Then computer vision algorithms analyze what they see, identifying objects, recognizing faces, and understanding where things are located. It then creates a 3D map of that space, allowing digital elements like virtual furniture or instructions to be placed precisely in the user's view. Think about trying on clothes virtually without actually going into a store, or playing Pokémon Go by seeing Pokémon appear in your own backyard. These technologies are transforming industries and creating completely new ways to interact with our surroundings. Okay, let's talk about how we're bringing computer vision into the world of virtual reality. VR vision systems are all about making virtual environments feel as real as possible, mimicking how our eyes and brains work. They are a really exciting blend of technologies, particularly NLP, computer vision, and increasingly multimodal AI, which means combining different types of data like sight and sound. We use things like stereo cameras or LiDAR to build 3D maps of the VR space, basically figuring out what's there and where it is. Then we use computer vision models to identify objects in the scene, saying that's a chair, for example. Eye tracking is also critical. Knowing exactly where someone is looking helps us render things more realistically and make interactions smoother. And because users often interact with VR using voice or text, NLP plays a big role too, allowing them to give commands like change the lighting. There are some powerful models involved: CNN for object detection, RNN and transformers for handling sequences of data like eye movements, and multimodal fusion models that combine all these different streams of information. This technology is already being used in things like realistic training simulations, making experiences more accessible for people with disabilities, and creating even more immersive games and entertainment. Okay, so let's talk about Edge AI. It's a really exciting development. Basically, instead of sending all the data from our cameras to a cloud server for processing, we're running the AI directly on those devices themselves. Think of it like having a mini brain right in the camera. This dramatically reduces lag, meaning things happen much faster, super important for things like self-driving cars or robots needing to react instantly. It also saves bandwidth and keeps data more secure. We're seeing this used everywhere, from smart security cameras that can spot people and vehicles without sending everything to the cloud, all the way to industrial robots checking for defects on a production line in real time. Let's talk about on-device computer vision. Basically, it's running AI for image and video processing directly on your device like your phone or a smartwatch instead of sending everything to the cloud. This makes things much faster because there's no lag due to network requests, and it also keeps your data private. The magic happens through edge computing, where we use pre-trained models that have been specifically tweaked for smaller devices. We often use something called quantization to shrink those models down even further, and then leverage hardware accelerators like MPU or GPU within the device itself to really speed things up. You'll find this being used in a ton of cool apps, from instantly recognizing objects in your photos to powering augmented reality experiences and even controlling your smart home with gestures. Okay, let's talk about getting these powerful AI models to respond fast. Real-time applications like chatbots or self-driving cars need quick answers. That's where inference optimization comes in. We can speed things up through several clever techniques. First, we have model quantization. Essentially, we reduce the precision of all those numbers inside the model, making it smaller and faster. Then there's pruning, which is like trimming away unnecessary connections to make the model leaner. Knowledge distillation lets us train a smaller, quicker model that still learns from a bigger one. And finally, utilizing hardware accelerators, such as GPU or TPU, can dramatically boost performance. It's important to remember that this isn't a one-time fix. You need to keep monitoring and tweaking your models to get the best possible speed. Okay, so let's talk about how we actually measure what's happening with computer vision models. To do that, we rely heavily on benchmark datasets. Think of them as standardized tests for our AI algorithms. We have a couple of really important ones, COCO and ImageNet. COCO is great because it deals with more complex scenes like detecting objects within a scene and even describing what's going on in an image. And then there's ImageNet, which is absolutely massive, primarily used for just classifying images into different categories. Using these datasets lets us compare how well different models are performing against each other. It's all about objective measurements and making sure everyone's playing by the same rules. Okay, let's talk about how we know our computer vision models are actually doing a good job. We don't just look at yes or no answers. Accuracy alone isn't always enough. There are several key metrics we use to get a more complete picture. Accuracy is the most straightforward, simply telling us what percentage of predictions were correct. But when you have an uneven distribution of classes in your data, like maybe there are way more images of cats than dogs, you need something else. Precision tells us how reliable our positive predictions are, while recall shows us if we're catching all the actual positives. Then there's a phone score, which balances these two concepts. For object detection tasks, intersection over union, or EOU, is really important. It measures how well our predicted bounding boxes overlap with the actual ones. And finally, mean average precision, or MAP, is a popular metric for this type of task as well. Ultimately, choosing the right metric depends on what you're trying to achieve and the characteristics of your data. Let's talk about data augmentation and computer vision. It's a really clever trick we use when we don't have tons of training images. Basically, we take our existing photos and slightly tweak them, maybe rotate them, flip them, change the brightness. We're creating new variations without actually taking brand new pictures. This helps the model learn to recognize objects even if they appear in different orientations or lighting conditions. Techniques like geometric transformations, color jittering, and mixing images together are all common ways to do this. It's like giving your model a wider view of what it needs to detect. Okay, let's talk about how AI is tackling videos. Specifically, we're looking at two really powerful capabilities: creating short summaries and generating smart captions. First up, there are different ways to summarize a video. You can either have the AI asterisk rewrite asterisk the key points into new sentences, called abstractive summarization, or simply pull out the most important existing sentences from the transcript, which is called extractive summarization. Then, when it comes to captions, we've got automatic speech recognition, or ASR, that converts spoken audio into text. And increasingly, these systems are getting really smart by combining ASR with computer vision, so they actually look at what's happening on screen and generate captions describing the visuals too. Pretty neat, right? Okay, so let's talk about recognizing what people are doing in videos. It's actually really tricky. You can't just look at one image and know what someone is up to. We need AI that understands how actions unfold over time. Initially, convolutional neural networks were used to extract features from individual frames, but those alone aren't enough because they don't capture the sequence of events. Recurrent neural networks like LSTMs are great at handling sequences, and 3D CNN treat a video as a three-dimensional volume, essentially learning how things move in space and time simultaneously. More recently, transformers have emerged as a powerful tool for action recognition, offering even better ways to understand long-term dependencies within the video. We've seen some really impressive architectures like A3D, which builds on 2D CNN, and Time S-Former, which uses transformers. Okay, let's talk about traffic sign recognition. Traditionally, recognizing signs was a complex process relying on manually created rules. But modern systems are much smarter. They use computer vision to quickly spot the sign in an image. Think of it like a super-fast visual search engine. Then, we bring in natural language processing. Instead of just seeing a shape, the system analyzes the textual description of that sign, allowing it to understand what the sign actually means. For example, it knows a red octagon isn't just a red octagon, it's an instruction to stop. This combination is key for things like self-driving cars and improving road safety. Okay, so let's talk about how self-driving cars actually see. It's a really complex system built around three core areas: computer vision, which is basically teaching the car to interpret images like we do; sensor fusion, where data from different sensors like cameras and LiDAR are combined to create a more reliable picture of what's happening around it; and increasingly, natural language processing, helping the vehicle understand instructions or contextual information. It's all about building a comprehensive understanding of the environment. Okay, so let's dive into crowd counting. It's a really interesting area where AI is making a huge difference. Historically, people counted crowds by hand, which is obviously slow and unreliable. But now, computer vision comes to the rescue. We use models like YOLO or Detectronto to spot individual people in images. However, simply knowing how many people are there isn't always enough. We need to understand density. Density estimation techniques like kernel density estimation or adapting models like SciMask tell us how likely a person is to be at each point in the image, basically how crowded it is. And here's the cool part: we can combine that visual information with other data, like video footage showing movement patterns or even audio cues, to get an even more accurate count. This technology has tons of applications, from optimizing staffing at big events and understanding customer flow in stores, all the way to improving public safety during emergencies. Okay, so let's dive into using AI with satellite and aerial images. It's pretty amazing what we can do now. We're primarily looking at techniques like object detection, basically training the computer to spot things like buildings or roads in these huge pictures, and semantic segmentation, which is a more detailed approach where every single pixel gets classified. Think of it as labeling an entire image with what its asterisk is asterisk. Finally, change detection helps us track how things are evolving over time, spotting areas that have been developed or damaged. But the real power comes from combining this visual data with natural language processing. We can use NLP to understand reports and articles related to these images, giving us a much richer understanding of what's happening on the ground. It's like giving the AI context. Okay, so let's talk about infrared and thermal imaging. These aren't your average cameras. They actually detect heat, which is invisible to us. Think of it like this: everything emits infrared radiation, even you. Specialized sensors pick up these heat signatures, creating images that show temperature variations. We use microbolometers and phosphor-based sensors for this. It's incredibly useful in building diagnostics, spotting insulation problems or heat leaks, and also plays a big role in medical imaging, helping doctors identify issues like inflammation or blood flow. Industries are using it to monitor equipment and prevent breakdowns, and even wildlife researchers use it to observe animals without causing stress. The really cool thing is that infrared data can be combined with computer vision. Imagine knowing exactly where the heat source is in a building thanks to both technologies. Okay, let's dive into hyperspectral imaging. Think of it as taking a really detailed rainbow picture of something. Instead of just one color like a regular camera, it captures data across hundreds of narrow bands. This creates an incredibly rich spectral signature that tells us exactly what the object is made of and its properties. We use techniques like spectral mixing to break down this data into its different components, and dimensionality reduction helps manage all those details. It's used in pretty amazing places, from boosting crop yields through precision agriculture to monitoring our environment and even analyzing materials for quality control. Okay, let's talk about biomedical image segmentation, a really important area in healthcare AI. Essentially, it's like drawing boundaries around things within medical images, like organs or tumors. We use different techniques to do this, from simple methods like thresholding, where we just pick a brightness level and say anything above that is part of the object, all the way up to sophisticated deep learning models like UNet and DeepLab V+. These models learn to automatically identify what's important in the image. And why is this useful? Well, it's used for everything from helping doctors diagnose diseases more accurately to planning treatments and tracking how a disease progresses over time. Pretty powerful stuff. Okay, let's talk about deepfake detection. These are basically convincingly fake videos or images, and they're getting really good at fooling people. So how do we spot them? Well, there are a few key strategies. First, we look for visual glitches, unusual blinking patterns, lighting issues, and distortions around the edges of faces. Then, we check if the lip movements match the audio, which is often where deepfakes stumble. Finally, we analyze how the face moves over time. Do the expressions flow naturally? Researchers are using some really clever techniques like autoencoders to spot inconsistencies, and even GAN discriminators trained specifically to identify fake content. Combining computer vision with natural language processing is key to tackling this challenge effectively. Okay, so let's talk about how we can get computers to recognize emotions in images. It's a surprisingly complex problem. Basically, we start by finding faces within the picture using computer vision techniques. Then, powerful neural networks, specifically convolutional neural networks or CNN, are used to automatically learn what features in those images indicate different emotions like happiness, sadness, anger, or surprise. These CNN are trained on massive datasets of labeled facial expressions. Think of it as teaching a computer to see the signs of each emotion. We then use a classifier to take all that information and give an overall emotional label to the image. Okay, let's talk about visual relationship detection, a really cool area where we're teaching computers to see and understand how things connect in images and videos. It goes beyond just recognizing what asterisk is there. It's about figuring out how those things are related. We use techniques like object detection, which pinpoints individual objects, and scene graph generation, basically building a map of the scene showing all the objects and their connections, like a man riding a bicycle. Graph neural networks are key here for reasoning about these relationships. Recently, we've seen transformer models bringing that same powerful learning ability from text into the visual world. This is already being used in some incredible applications, everything from helping self-driving cars navigate safely by understanding pedestrian interactions to enabling robots to actually do things based on their understanding of connections between objects. Okay, let's talk about zero-shot learning in computer vision. Imagine you're building a system to recognize all sorts of animals, but you only have pictures of lions, tigers, and bears. That's a lot of labeling. Zero-shot learning changes the game completely. Instead of needing labeled data for every single animal, we use something called semantic embeddings, basically descriptions like striped, flying, or a mammal. The model learns to connect these descriptions to what it sees in images. So, if you show it a picture of a panda and describe it as black and white, large cat, it can use its knowledge to correctly identify it, even though it's never seen a panda before. It's like giving the computer clues instead of just showing it examples. Okay, so we're moving beyond just saying this is a dog. Multi-label classification lets us identify multiple things in an image at once. Think about a photo of a park. It could be labeled as showing both a dog and an outdoor scene, or even recognizing the presence of trees and people. The models we use, like CNN, are really good at spotting visual patterns. Instead of just predicting one category, they predict probabilities for every possible label, and a threshold helps us decide which ones to include in the final result. It's super useful when you need detailed information about what's going on in an image, things like medical imaging or even analyzing satellite photos. Let's talk about something really important in computer vision, figuring out when a model is seeing something it doesn't understand. We call that out of distribution or OOD detection. Basically, your typical image recognition model does great on things it's been trained on: cats, dogs, cars, you name it. But what happens when it sees, say, a completely new type of animal, or an unusual scene? That's where OOD detection comes in. There are several ways to do this. One common approach is using reconstruction. Error models like VAE try to rebuild the image they see, and if something's weird, the reconstruction will be poor. Another technique looks at confidence scores. If a model suddenly loses its certainty about what it's seeing, that could mean it's encountering an OOD sample. Finally, generative models, like GAN, can help us assess how well new images fit into the learned distribution. Okay, so let's talk about graph neural networks for vision. You know how convolutional neural networks are amazing at spotting details within an image, but they can sometimes struggle to understand the bigger picture, how things relate to each other in a scene. GNN changed that. They treat images like graphs, with pixels as nodes and connections between them based on where they are located. This allows the network to talk to every part of the image and build up a really good understanding of the whole scene. We represent each pixel with features like its color, and then link related pixels together. The GNN then passes information between these connected nodes, learning how everything fits together. It's great for things like figuring out what's in a complex photo or identifying relationships between objects. Okay, so we're shifting gears and looking at how transformers are changing computer vision. For a long time, CNN were king, but they struggled with understanding relationships between distant objects in an image. Transformers solve this problem by using something called self-attention. Think of it like this: instead of just looking at its immediate neighbors, the model can directly compare any part of the image to every other part. This is a huge leap forward. The vision transformer, or VIT, takes this idea and applies it directly to images by breaking them up into patches, treating those patches like words in a sentence, and then feeding them through a regular transformer encoder. Positional embeddings are added so the model knows where things are located. It's a surprisingly effective approach and has led to some really impressive results. Okay, let's start with the basics of multimodal AI. For a long time, AI were pretty good at just one thing, like reading text or recognizing images. But we understand the world using our senses, right? Multimodal AI is all about mimicking that. It's about taking information from different sources, let's say text and images, and combining them to get a much deeper understanding than you could get with just one of those things alone. For example, looking at an image with its caption can give you way more context. We'll see some examples like using audio and video together, or even wearable sensor data combined with written notes. Okay, let's talk about how we actually put all these different types of data, text, images, sound, you name it, together in a way that AI can really understand. There are a few main strategies. We could start by combining everything at the very beginning, like stacking all the raw image pixels and words into one big blob before feeding them to our model. That's called early fusion. Alternatively, we might let each modality process its data separately with its own specialized architecture and then bring those results together later on. That's intermediate fusion. Finally, we could have each modality create its own prediction and then combine those predictions at the end, like averaging them out. Different approaches work better for different tasks, like visual question answering where you're combining images and questions, or even sentiment analysis in videos, considering both what people say and how they look. Okay, let's talk about vision language models. They're a really exciting development at the intersection of computer vision and natural language processing. Basically, these models are designed to understand and interact with the world in a more holistic way by combining what we see with what we say. They've moved beyond just looking at images or just reading text. Now they can do both. We'll cover some key techniques like image captioning, automatically generating descriptions of pictures, visual question answering, where you ask an AI a question about an image and it tries to answer it, and even text-to-image generation, where you give the model a description and it creates an actual picture. Some well-known models include Clip, which learns how images and text relate to each other, Flamingo, that's really good at visual reasoning, and Blip, which leverages weakly labeled image-text pairs. It's all about bridging the gap between what we see and what we communicate. Okay, let's talk about Clip. It's a really clever AI model developed by OpenAI that tackles the challenge of understanding how text and images relate to each other. Basically, instead of teaching an AI to do something specific like identifying objects in pictures, Clip learns the fundamental connection between them. It does this using contrastive learning. It figures out which image best matches a given text description, and vice versa. It uses two separate encoders, one for images and another for text, but they both end up projecting everything into a single shared space where similar things are close together. This makes it incredibly versatile. It's used in things like advanced image search, zero-shot classification, meaning it can categorize images without being specifically trained on those categories, and even retrieving relevant images based on textual queries. Okay, let's talk about DALL-E. It's a series of AI models developed by OpenAI that are basically magic. They turn words into incredible images. The first version, DALL-E 1, was the initial proof of concept, showing that you could give it a really detailed description and get something pretty amazing back. Then came DALL-E 2, which took things up a notch with much higher quality and more realistic results. And now we have DALL-E 3. It's even smarter thanks to ChatGPT integration, making prompt creation way easier and the images even better. It's really impressive how these models can understand your instructions and create exactly what you envision. Okay, so let's talk about image captioning and how transformers are really changing the game here. Before transformers, we typically used CNN to analyze images, which were good at spotting local features but often struggled with understanding the bigger picture, like how a cat relates to a ball in the scene. Transformers, on the other hand, use something called self-attention that lets them look at every part of the image all at once and understand those long-range dependencies really effectively. Basically, they build a much richer understanding of the visual context, leading to captions that are more accurate and descriptive. Let's dive into visual question answering, or VQA. It's a really fascinating area where we teach computers to actually understand images and answer questions about them in natural language. Basically, we feed an image and a question to the system, and it needs to figure out the right response. The process starts with using a CNN. Think of it like a sophisticated digital eye to analyze the image and create a numerical representation of what's visible. Simultaneously, another part of the system, often an RNN or transformer, processes the question to understand its meaning. Then, these two views of the information, the image features and the question context, are combined, usually using something called attention, allowing the model to focus on the most relevant parts of both. Finally, it predicts the best answer, whether that's from a list of options or even generating a sentence directly. It's like teaching a computer to see and understand, just like we do. Pretty cool, right? Okay, let's talk about cross-modal retrieval. Basically, we're building AI systems that can really understand how different types of information like text and images relate to each other. The key is creating embeddings, which are like numerical fingerprints for both text and pictures, capturing their meaning. Then, using a technique called contrastive learning, the system learns to group related items together. Think of it as teaching the AI what's similar and what isn't. So, if you ask something like a red apple on a table, the system can find an image that matches, even if it wasn't specifically described with those words initially. It's all about finding connections between different data types. Okay, so let's talk about turning words into pictures. It's really cool. This is called text-to-image generation, and it's a super exciting area of AI. Basically, we use powerful language models like the ones that write stories or answer questions to understand exactly what you want to see in an image. Then a separate model, often based on something called a diffusion process, takes that understanding and builds the image from scratch, starting with random noise and slowly refining it until it matches your description. Diffusion models are currently the most popular because they create really high-quality images. You'll find these techniques used everywhere, from creating unique artwork to helping designers quickly visualize their ideas. Okay, so let's talk about turning words into moving pictures. We're looking at a really exciting area called text-to-video generation. The core idea is that we can describe a scene in writing, and an AI will then create a video of it. It's all based on diffusion models. Think of them as learning to undo noise to reconstruct images, but now applied to videos frame by frame. Models like Mako Video and Imagen Video are leading the way, using transformer architectures to understand how words relate to visuals. Basically, they start with a noisy image and iteratively refine it based on the text prompt you give them. Really powerful stuff. Okay, so let's talk about combining speech and images. It's a really fascinating area. We're moving beyond just recognizing individual sounds or pictures. We want machines to understand the connection between them. Think of models like Clip that learn how images and text relate to each other, creating a powerful starting point. We also have techniques like visual linguistic pre-training, where systems learn to represent both visuals and text in a shared space. It's about searching for things, a red car, for example, using either an audio clip or an image, and then retrieving the relevant data. And, of course, there's automatic captioning, teaching machines to describe what they see and hear. There are some really impressive models out there like BLIP-2 and Flamingo that are pushing the boundaries of what's possible with this kind of multimodal learning. It's a field ripe with potential, especially when it comes to things like helping people with disabilities or even creating new types of content. Okay, let's talk about video captioning. These models are basically teaching computers to read videos and turn what they see into text. First, a computer vision system analyzes each frame of the video using things like CNN to identify objects, people, and actions. Then often an LSTM or transformer steps in. It looks at how these visual elements change over time, understanding the sequence of events. Finally, another part of the model uses NLP to string together words and create a caption that describes everything happening. There are some really cool models out there like Show and Tell, Imagen Video, and Flamingo. It's a rapidly developing field. Okay, let's talk about visual dialogue systems. These are some really cool AI systems that combine the power of both natural language processing and computer vision. Essentially, they allow you to have a conversation with an image or describe what you see to get answers. They work by first using computer vision to understand what's in an image, identifying objects and scenes. Then, natural language processing comes into play to process your questions or statements. Finally, a fusion component combines these two streams of information, allowing the system to reason about the visual data and generate a helpful response. You might see this used in virtual assistants that can answer questions about products you're looking at in pictures, or even helping people with vision impairments navigate their environment. Okay, so let's talk about recognizing emotions with AI. We're moving beyond just reading text or looking at a face. We want machines to understand how people are feeling. Multimodal emotion recognition is all about combining information from different sources. Think of it like this. If you were trying to figure out someone's mood, you wouldn't just rely on their words. You'd also look at their facial expressions and maybe even listen to the way they speak. That's what we're doing here. We use computer vision to analyze faces, NLP to understand text, and audio analysis to pick up on subtle changes in speech. Powerful models like CNN combined with RNN are often used. Basically, one part of the system looks at images or audio, while another analyzes text. And don't forget about transformers. It's a really exciting field with some amazing applications, from helping chatbots understand frustrated customers to potentially even assisting in mental health monitoring. Okay, let's dive into multimodal sentiment analysis. Basically, we're moving beyond just looking at what people say, which is great, and trying to understand how they feel by considering other cues. Think about a customer review. The words might be positive, but the tone of voice during a phone call could reveal underlying frustration. MSA combines natural language processing for text analysis, computer vision to detect facial expressions, and audio analysis to pick up on vocal tones. It's like piecing together the whole picture to get a much more accurate read on someone's emotional state. Okay, so let's talk about speech to text combined with images. It's a really cool way to make AI even more helpful and intuitive. Basically, you give the system a command using your voice, and it converts that into text. But here's where it gets interesting. That text is then used to find related pictures from a database. Think of it like asking, "Show me a picture of a red apple," and instantly getting an image displayed alongside your answer. This is useful for all sorts of things, like helping people who are blind understand what's around them, or even making interactive tutorials easier to follow. Okay, let's dive into audio-visual speech recognition, or AVSR. Basically, it's like giving our speech recognition systems a bit of a superpower. They can now look at what people are doing with their mouths while listening to their voices. Traditional speech recognition just listens to the sound itself, but that can be tricky because noise and accents can throw things off. AVSR combines audio data, like MFCCs representing the sound waves, with visual information from video feeds analyzing lip movements and facial expressions. Then, clever models, often using CNN for visuals and RNN or transformers for speech, fuse these two streams of data to create a much more accurate picture of what's being said. It's all about combining strengths. Okay, so let's talk about translating languages using AI. Traditional machine translation really focused on just text, but humans use *, more than words. We look at pictures, we listen to voices. It gives us context that helps us understand what's going on. Multimodal machine translation is all about teaching AI to do the same thing. It's basically a three-step process. First, NLP analyzes the original text to figure out its meaning and structure. Then, computer vision comes in and examines any accompanying images or videos, identifying objects and understanding the scene. Finally, these two pieces of information are combined using sophisticated techniques like transformers. Think of it as AI blending both textual and visual clues to create a really accurate translation. Okay, so now we move into how AI can actually understand information in a more holistic way. We're talking about multimodal representation learning, which is all about building a single, shared understanding of data that comes from different sources like text and images. Instead of treating each source separately, like just reading a sentence or looking at an image, we want the model to see how they relate. A really useful technique here is contrastive learning, where we train the model to recognize when things are related and separate them when they aren't. This helps it build these connections between different types of data. We're also seeing transformers becoming increasingly popular for this task because their attention mechanisms allow them to focus on the most relevant parts of each modality when building a combined representation. Imagine a model that can link an image of an apple directly to the word red. That's the kind of understanding we're after. Okay, let's dive into multimodal transformers. These models are a really exciting development because they move beyond the idea that NLP and computer vision need to work in separate silos. They actually learn how text and images relate to each other, which opens up some seriously cool possibilities. Specifically, we're talking about models like LXMERT and VisualBERT. LXMERT treats both text and image regions as part of a single sequence for processing, leveraging the transformer architecture for really efficient understanding. And VisualBERT is essentially a BERT model that's been adapted to handle images alongside text, making it great at tasks like answering questions about pictures. Okay, so we're talking about masked multimodal modeling. It's a really clever way to get AI systems to understand how different types of data relate to each other. Basically, we take parts of the input away and train the model to figure out what was missing. It's like a fill-in-the-blanks puzzle, but with images, text, or even audio. Models like Vicuna and Flamingo are great examples of this in action, allowing them to do things like answer questions about pictures or generate captions that perfectly match an image. Pretty cool, right? Okay, let's talk about contrastive learning. It's a really clever technique gaining serious traction in multimodal AI. Basically, we want our models to understand how different types of data relate to each other, like images and their descriptions. The idea is simple. A model learns to bring similar things closer together in its brain, like when an image and its caption go hand in hand. Conversely, it pushes dissimilar things further apart. It's a bit like a similarity game for computers. This approach leads to better alignment between different data types and makes models more robust, meaning they can still function well even if some information is missing or noisy. Okay, so we're moving into the exciting world of multimodal generative models. These aren't your typical AI systems that just focus on one type of data like text or images. Instead, they're designed to combine information from multiple sources, letting them truly understand and create in a more holistic way. Think about it, humans often use all our senses when we communicate and perceive the world. These models try to mimic that process. We've got examples like Clip, which learns to connect images with their associated text descriptions. Then there's DALL-E 2 and Midjourney, famous for creating incredible images from just a written prompt. And Flamingo is an especially impressive model capable of quickly adapting to new tasks when given only a few examples. Essentially, they all share a common understanding of space where different types of data relate to each other, making them far more versatile and creative than single-modality systems. Okay, so let's talk about building a structured understanding of images. We're going to look at scene graph generation, basically teaching computers to see relationships just like we do. First, the computer vision part kicks in and identifies all the objects it sees in an image, using models like YOLO or faster CNN. Then an NLP model comes into play, figuring out how those objects are connected, who's doing what to whom. Think person riding a bicycle or dog chasing a ball. Finally, all that information gets organized as a graph, with objects as nodes and the connections between them as edges. Graph convolutional networks are often used to really dig into these scenes and learn from the relationships we've identified. Okay, so we're now looking at how AI can actually understand scenes it's seeing, not just recognize individual objects. It's about going beyond simple object detection and grasping the overall context. We start with techniques like image captioning, which is where models automatically generate descriptions of images. Then we move into visual question answering, where you can ask an AI a question about an image, and it needs to understand both the picture and your query. Models like Clip are really key here because they create a shared space for text and visuals so the AI can genuinely reason between them. Think about how that could be used in robotics or even helping people with visual impairments. It opens up some amazing possibilities. Okay, so we're moving past just looking at things with computer vision or reading words with NLP. We're now focusing on building AI that truly understands the connections between them. This technique, called knowledge-grounded multimodal generation, is all about giving these models a world model. It starts by figuring out what information from sources like Wikipedia or structured databases relates to your initial text or image input. Then it combines the data coming in, text and images, and finds how they're connected. Finally, based on this combined understanding, the AI generates something new that's grounded in both the original inputs ** the retrieved knowledge. It's like giving the AI context beyond just what it directly sees or reads. Okay, let's dive into zero-shot learning. It's a really cool concept in multimodal AI. Basically, we're giving these models the ability to tackle tasks they've never explicitly seen before. Imagine teaching a child that knows how to add numbers and then asking them to solve a complex word problem that's similar to what zero-shot learning achieves. It uses existing knowledge from different sources like text and images to generalize incredibly well. The key is prompting. We use textual descriptions, often called prompts, to guide the model, and it leverages its understanding of language and visual information to generate outputs, even if those specific inputs haven't been part of its training data. Okay, so we've been looking at how NLP and computer vision are coming together in AI, but things are getting even more sophisticated. Now, we're moving into the realm of multimodal reasoning systems, basically AI that can actually think by combining information from different sources. Think about it like this: instead of just seeing a picture or reading a description, an AI system can use both to understand something better. We're talking about pulling together data from things like text, images, and videos, and even audio. There are several ways we fuse all that information, sometimes combining the raw data right at the start, other times making predictions with each source separately and then blending them later, or combining representations as we build the model. Ultimately, models like transformers and graph neural networks help connect these different pieces of information so they can actually reason about what's going on. It's a really exciting area, and it's leading to some amazing applications, from robots that understand instructions with visual cues to more intelligent human-computer interactions, and even better medical diagnosis. Okay, let's talk about multimodal explainable AI. Think about how we naturally understand the world. We use all our senses. Multimodal AI is similar. It's about feeding models information from multiple sources like text, images, and even audio or video to get a much deeper understanding than if we only focused on one type of data. And because it's complex, explainable AI becomes really important. We need to know why the model made a certain decision, not just that it did. There are some exciting techniques like visual question answering and video captioning with attention. These models learn to connect what they see with what they read. And then we're seeing powerful multimodal transformers emerging that can really fuse all this information together. It's still a challenging field, dealing with different types of data, making sure everything is accurate, and ensuring fairness across those modalities. Okay, let's talk about a really important aspect of multimodal AI: fairness and bias. These models are amazing because they can understand the world in multiple ways, combining text, images, sounds, and more. But just like any system built on data, they inherit biases from that data. Think about it: if an image dataset mostly shows people from one culture, the model might not perform as well for other cultures. And these biases aren't always obvious. They can come from how the models are designed, or even how humans label the data in the first place. It's crucial to understand where these biases originate, and then we need to actively work to mitigate them. We can do this by carefully examining our datasets, creating more balanced information, using training methods that specifically consider fairness, and trying to understand why a model is making certain decisions so we can tackle the root causes of any unfairness. Okay, let's talk about something really important: the ethics of multimodal AI. As we're combining information from all sorts of sources, text, pictures, sounds, you name it, we need to be incredibly careful. There are some big ethical challenges that could arise. One major issue is bias. If the data we feed these models isn't fair, they will learn and amplify those biases. Another concern is privacy. Combining multiple datasets can expose sensitive personal information more easily than ever before. And then there's the potential for misuse. Think about incredibly realistic fake videos or images designed to mislead people. Finally, a lot of these models are very complex, making it hard to understand why they make certain decisions, which makes it even harder to catch problems early on. So, Developing fair evaluation methods, strong data policies, and ways to make AI more transparent is absolutely key if we want to use this technology responsibly. Okay, let's talk about a really interesting and potentially concerning aspect of multimodal AI adversarial attacks. Basically, these are cleverly designed inputs that try to fool our models into making mistakes. Think of it like an attacker trying to trick a security system. We can categorize these attacks: data poisoning, where the training data itself is corrupted; evasion attacks, which happen during use, like adding a tiny sticker to a picture to cause misclassification; and transferability attacks. A single attack on one modality might work against the whole model even if that specific change wasn't there initially. Multimodal models are complex because they have to juggle information from multiple sources, making them vulnerable in unique ways. Different modalities like text versus images can be more or less susceptible to these tricks. Okay, so let's talk about some really important datasets that are driving progress in multimodal AI. We've got VQA, which is all about answering questions about images. Think, what color is the dog? The next one, Flick30, has thousands of photos each with multiple captions describing what's going on in the picture, perfect for teaching a model to connect visuals and words. And finally, MS-Coco. It's a huge collection of labeled images that we use for all sorts of things like generating captions or identifying objects within them. These datasets are vital because they give us the ground truth data needed to train and test our AI models. Okay, so when we're building these multimodal AI systems combining things like text and images, it's really important to understand how well they're actually working. Simply looking at a single accuracy number isn't enough. We need some specific metrics that tell us about the integration of different types of data. Things like Blue Score, which measures similarity between captions and what the model generates, can be useful. Then there's intersection over union, good for tasks where we have overlapping information like bounding boxes and images. Flip Score is also getting popular because it looks at how well the model's understanding of text and images aligns. And let's not forget human evaluation, often a critical part of assessing the quality, especially when things are subjective. Finally, always consider metrics that directly relate to your specific application's goals. Let's talk about how all this is being applied in healthcare. We're seeing some incredibly exciting developments thanks to the combination of NLP, computer vision, and multimodal AI. Think about it, doctors are using NLP to understand what's written in patient notes, which can be really helpful for spotting patterns and potential issues. Simultaneously, computer vision is revolutionizing image analysis, allowing us to detect things like tumors and X-rays with incredible precision. That the real magic happens when we combine these technologies. That's where multimodal AI comes in. It pulls together data from different sources, patient notes, images, sensor readings to give a much more complete picture of what's going on with an individual. And it's already being used for things like early disease detection, remote monitoring programs, and even virtual assistants that can help patients manage their health. Okay, let's talk about smart home assistants. They're getting way more intelligent. Traditionally, these assistants relied just on your voice commands with NLP. But today's systems are going a huge step further. They're using computer vision to see what's happening around them and even integrating data from all sorts of sensors in your house like thermostats and motion detectors. Essentially, they're combining all this information to really understand your needs, not just respond to specific words. Think about it. You say it's cold, and the assistant doesn't just look for that phrase, it uses its vision to check if you're bundled up, combines that with temperature readings from a sensor to confirm things are chilly, and then proactively turns on the heater all without any extra instruction. Pretty neat, right? Okay, let's talk about how AI is transforming surveillance. We're moving beyond just looking at video. We're actually combining different types of data to create a much smarter security system. Think of it like this. Your standard cameras are still important. Computer vision helps us identify objects and people. But then we add an audio analysis using NLP, so the system can understand what's being said, even if there's background noise. And finally, we integrate data from things like motion sensors or environmental readings to get a really complete picture of what's happening. It's not just about seeing, it's about understanding . Okay, so this slide is all about how we're moving beyond just typing commands or uploading pictures to interact with AI. We're starting to see incredible systems that understand us in a much more complete way. It's about combining different types of input like voice, what the camera sees, and even how you feel . Think smart homes where your voice controls everything, assistive technology helping people communicate through sign language, or robots responding to your gestures and instructions. The key is that these interfaces aren't just reacting, they're learning about you and anticipating your needs based on all the data they're collecting. Okay, let's dive into how multimodal AI is transforming e-commerce. Basically, we're taking the best of natural language processing, computer vision, and even audio analysis to create a more intuitive shopping experience. Think about it: when you look for something online, you might start with a text search, but then you want to see images. These systems can understand what you're saying and what you're looking at simultaneously. For instance, they can analyze product reviews to give you an accurate sense of quality, or instantly identify products from uploaded pictures for visual searches. Plus, AI-powered chatbots are getting smarter because they are now equipped to handle more complex questions that involve both words and visuals, like, is this dress available in blue, accompanied by a picture. Okay, let's talk about how this multimodal AI magic is being put to work in real industries. Think about manufacturing companies are using it to predict when machines might break down before they actually do, saving tons of money and preventing production delays. In retail, retailers are analyzing what customers are looking at combined with their past purchases to give them incredibly personalized recommendations. And healthcare is seeing huge advancements too. AI can now analyze medical images alongside patient records to help doctors spot problems earlier. Even logistics like self-driving trucks or robots in warehouses benefit from combining various types of sensor data for a more complete view. Okay, let's shift gears to a really exciting area: multimodal edge AI. Basically, we're moving beyond just using one sense like computer vision or natural language processing to tackle problems that require all the sensors working together. Think about autonomous vehicles. They need to see the road with cameras, but also hear approaching traffic and even feel the road surface through sensors. Edge AI is crucial here because it means we can process this data locally, closer to where it's collected, which cuts down on delays and keeps sensitive information private. We're using techniques like sensor fusion, combining data from cameras, microphones, and other devices, and cross-modal attention mechanisms so models know what's most important for the task. For example, linking a specific sound to its visual context. It's being used in some really cool applications like smart surveillance systems that can spot unusual behavior by analyzing video and audio, or even robots navigating complex environments using sight and touch. Okay, let's talk about scaling these really cool multimodal AI systems. Basically, we've moved past just using one type of data like text or images alone and are now building systems that can understand and respond to information from many sources at once. But running these complex models is a huge undertaking. We need to think seriously about how efficiently we're processing all this data. That means figuring out the best way to combine different pieces of information, using powerful hardware like TPU and GPU, splitting up the work across multiple computers if necessary, and even adjusting how much data we process at once, dynamically changing the batch size as needed. It's a bit of an engineering puzzle, but essential for making these multimodal models practical and usable in the real world. Okay, let's talk about getting multimodal AI out into the world, specifically how we deploy it for real-time applications. It's not just about building a great model. You need to think about how where it runs. The first step is gathering data from all your sources: audio, video, text, whatever's relevant. Then, you have to clean up the data and turn it into something the AI can understand, essentially extracting key features. Choosing the right model for the job is vital, and we often need to optimize these models to run quickly on hardware, which brings us to edge deployment. This means pushing the processing power directly onto devices like robots or drones so they can react instantly. A good example of this in action is a self-driving car. It's constantly using cameras, microphones, and GPS to make decisions all at once. Okay, so let's talk about how we're bringing these AI technologies into the cloud, specifically with cloud-native multimodal services. Think of it like this: instead of building and maintaining everything ourselves, we're using powerful platforms like AWS SageMaker or Google Vertex AI to handle the complex deployment of models that combine text, images, and more. These services provide managed environments that scale automatically as demand grows. And importantly, they streamline the flow of data, getting all those different types of information into our systems efficiently. Finally, robust API management allows us to easily expose these multimodal capabilities to other applications, speeding up development and making it simpler than ever to integrate AI into your projects. Okay, so let's talk about chatbots that are actually smart. These aren't just responding to typed words. They're using a combination of tools to really understand what you're asking. First, we have NLP. Basically, the chatbot reads your text and figures out what you mean, like understanding the context of your question. Then, computer vision comes in, letting the chatbot see things. Think about pointing at an item online and getting specific information instantly. And finally, voice recognition turns spoken words into text, while text-to-speech lets the bot respond back to you verbally. It's all about combining these different AI strengths for a truly intuitive conversation. Okay, let's talk about how large language models are now getting a visual sense. For years, NLP was all about words and computer vision focused on images. They worked in separate silos. But recently, models like GPT-4 Vision and Google's Gemini have been built to combine these two powerful areas. Basically, they take an image as input, use their vision capabilities to understand what's the picture, and then tie that understanding into their existing language knowledge. It's like having a really smart assistant that can not only read your text but also see it too. They can answer questions about images, generate descriptions, or even just tell you what they think is happening in a photo. GPT-4 Vision and Gemini are leading the charge here, showing us exactly what these multimodal models can do. Okay, so we've seen some amazing things with multimodal AI combining text, images, audio, you name it. But let's be honest, we're not quite there yet. A big challenge is getting all these different streams of information to work together smoothly. Specifically, keeping track of how things change over time, like in a conversation, is tricky. Then there's the problem of grounding, making sure the AI truly connects visual elements with their descriptions or sounds with images. We also need to be really careful about bias, because these datasets often reflect existing societal problems, and models can amplify those issues. Robustness is another concern. AI trained in one place might completely fail somewhere else. And finally, it's hard to know why a multimodal system makes the decisions that it does. We need more explainability. Okay, let's talk about what's next for how we interact with computers. The future is definitely multimodal. That means combining different types of information, like words, images, and even our senses, to give AI a much fuller picture of what's going on. We're moving towards experiences that feel more natural and intuitive, almost as if the technology anticipates your needs. Think about AI assistants that can understand not just what you say, but also how you say it, and even how you're feeling. And we'll see this happening with robots too. They'll be able to collaborate with us in new ways because they'll have a much better understanding of the world around them. Thank you for watching.